an entire system may be collapsed. That's why this particular structure is being avoided right now. This is a horizontal clearance between the bar structure, that is N plus DIH plus MA. N means the live part, from the live part to the ground potential, the distance between the live part and the ground potential, and DIH is some allowable distance, workable distance that has been kept as a factor of safety. And this MA, there is another allowable distance, but in our distribution system we don't afford that much of allowance, so we consider N plus DIH, N plus M only. DIH we cannot allow. And this is the upper portion, that is N plus DIV and 1440, but basically DIV is not allowed in the upper portion. We 1440 plus N we usually consider in case of horizontal clearance, and this we consider in case of vertical clearance. We usually consider N plus 1440 plus DIV, but in horizontal clearance we use N plus MA, not DIH. You will see it in the next portion. H is equal to N plus MA plus DIH, minimum phase to ground clearance, that is N, I have told you, that is 0.381 plus MA, that is the, suppose the ladder slips and falls down, so we can we should be given some allowance of area, so that without hampering any to the workable person or any instrument, the ladder can fall down easily. So in that case 1 meter we usually use, so 2.38 meter, 2.4 meter the center to center clearance we usually do that. But in case of, as because we don't have that allowance, DIH is always comes to 0. Now comes to lightning mast or the lightning stroke of the lightning protection, that is 25 meter plus lightning stick is 2.5 meter. The entire area, that the rectangle of the lightning mast, it creates DS. DS that means the area within which the entire 4 lightning mast can create, that is 8 into H minus HX. H means height of the mast, and HX is the height of the maximum height of the live part of the switchyard, and P is 1. P is a factor. P is 1 if height of the mast is less than 30 meter. When we do that, suppose this LM1, lightning mast 1, lightning mast 2, lightning mast 3, and lightning mast 4. So every lightning mast has got the power to create a circle where the lightning can be arrested, and that circle can be created with an radius of Rx. So lightning mast 1 create that circle, lightning mast 2 creates the circle, lightning mast 3 creates the circle, and lightning mast 4 creates the circle. And another astonishing thing is there, these circles altogether creates a circle in between them, and that is also protected from the lightning. So they can create 4 circles each, and that is with a radius of ROX. And altogether these circles can create another circle in between them, that is also protected from the lightning. So in that manner, if you see the height of the lightning mast is 16 meter, and height of the maximum live part of the switchyard is 8 meter, and then Rx comes 9.75 meter, and ROX comes 7.2175 meter. So with 4 lightning masts, we can almost cover the entire switchyard and outside portion, and that is the beauty. Now this is a case study of load flow study. Load flow study is very important. That is, we do in ETAP and MIPSCT software. We have taken a substation, is goal C in Bardwan. Install capacity is 2.63 and 1.10. Perspective peak load 2122 is considered as 19 MVA. Main 33 kV feeder from Mankor grid substation. ACSR dog conductor. Route length was 20.396. Number of 11 kV feeder is 7. Now you see the dog conductor specification: panther, wolf, dog, rabbit, weasel, and squirrel. 200 square mm, 150 square mm, 100 square mm, 50 square mm, 30 square mm, 20 square mm, and the maximum current capacity is given over here. So, and there is a GIS map. I just want to give you some idea. I don't want to discuss it thoroughly. Now it comes the load flow result. You see the Mankor GSS total MVA, which you can cater to the next 33 kV 11 kV substation, is 23.7 MVA, and current is 41.4.3 ampere. Now it is coming to the dog conductor single line, which is 20.396 apart from the GSS, this substation, 33 11 kV substation. The line loss comes to around 3.58 megawatt, and MVA is 3.7. Huge line loss, and as a result of which you see the voltage regulation, how poor it is. From 33 kV, it drops down to 26.45 kV because of the huge load on a single phase. Now, if you see the MVA, 23.7 MVA, we receive the power of 19 MVA, although current is same. That's 4 MVA is being lost through this line. Now, if we split the line in two different lines, now MVA is same. One is 11 MVA, one line draws the 11 MVA power, one line draws the 9.4 MVA power, one line draws 192 ampere current, and one line draws 172.1 ampere current to the line length. One is 22 kV line length, one is 20.396 line length, same line length. You see the voltage regulation, the voltage is almost 33 kV. Not 33 kV, it is 30.01 for one case, another case 30.11 for 33 kV bus. So huge voltage. From previously it was 26.45, the voltage regulation has been improved to 30.01. So that software analysis we usually do, that we come to know whether the second line for that particular substation is needed or not. Initially, at the inception, during the deliberation, I was showing why this design is needed from our part, and it is being expressed over here, how it is being done. Next, I am showing you the calculation of fault current of ATMAT design. It's very important. For 2 into 10 MVA, fault current is 10 kiloampere. 3 into 10 MVA, fault current is 14 kiloampere. Suppose it is being given, and there is a fault current calculation of ATMAT design, 132 kV grid fault substation. There is 3 into 50 MVA transformers, and it is a vector diagram. Impedance is 12.5%. Now it is feeding to a 33 kV substation, 2 into 10 MVA transformers, and where percent impedance is 8.15, DYN 11. So in that particular case, you see the calculation of fault current in ATMAT is very interesting. There is a base MVA of 100. Now fault current of 132 kV grid, MVA is 7201.867. Now equivalent per unit impedance of 33 kV grid is Z equivalent is MVA base by MVA fault current, that is 0.1389 per unit. Now if you come to the per unit impedance of the 132 by 33 kV 50 MVA power transformer, each individual transformer, that is ZTR1 PU, is ZTR1 into 100 by 50, that is 0.25 PU, that is a base MVA, and for that particular transformer, the capacity is 50, so it is coming to 100 by 50 into ZTR1, that is 0.25. Percentage impedance of 33 kV for 10 MVA transformer, the same formula, 100 by 10 by ZTR2, it is 8.15 PU. Now it is being fed to the calculation of fault current to the ATMAT design. You see the equivalent of per unit impedance up to the fault point, ZPU is equal to Z equivalent plus ZTRPU by 3, and ZTR1 PU by 3, ZTR2 PU by 2. If you do that calculation, the per unit equivalent impedance comes to 0.5047. So fault MVA comes to fault MVA base by ZPU, 100 by 0.5047, it comes around 198.13. Now this is the fault MVA. So this fault MVA creates the fault current 11 kV bus. So fault MVA by root 3 into 11, it comes about 10.4 kiloampere. That's how we calculate the entire fault level of a particular substation, and then we design the ATMAT. Suppose we consider the gravel of 2500 ohm meter, resistivity 0.1 meter of earth surface. We have already measured it. Fault current we consider is 14 kiloampere. Round conductor, we will use the flat of GI flat of 65 into 6 mm. It will be laid just below a 0.6 meter of the earth. And earth electrode, it is perforated GI pipe 3 meter long, 40 meter just 25 number such earth electrode we will be using. Soil resistivity is 10 ohm meter and switcher dimension is 30 meter by 18 meter. In that particular case, there is a step and touch potential. You know better. I don't want to discuss the step and it's a basic theory. Step and touch potential. So now the touch potential should be limit under tolerable limit. It is our main purpose, and state potential is also tolerable limit. It is our main purpose. Ground grid resistance should be below 2 ohm. So if we do it automatically through ETAP software, we get a design like this, where the art pit should be given, how much the 30 by 18 meters switch here, how the grid. So this is the result we usually see through the ETAP software. In case we put the system data in the software, that is 50 hertz, maybe 50 kg of weight, ambient temperature 40 degrees Celsius, total fault current is 14 as I've shown. This is the X by R 18, it is being neglected. Now the division factor and projection factor is 100%. Why it is 100%? We are considering that the feeding substation, the EHV substation, 132 by 33 kV substation is just beside the 33 kV substation. Although it is 20 kilometer apart, if it is 20 kilometer apart, fault level will be much lower. But we are considering that in the future, maybe another EHV substation may be coming up very nearby to the 33 kV substation. In that particular case, the fault level will be much higher than the calculated fault level right now. But in that particular, in that case, we can't dismantle the entire substation and again revamping the earth mass. It is not possible. It is not possible. That's why we consider how far the 33 kV, 132 by 33 kV substation is. We consider that this substation is always beside our 33 kV substation, and we consider the maximum fault level. That is, that's why it is considered 100. And fault duration we consider 3 seconds. Achha, I am just asking, I am audible to everybody?
Yes, sir, you are audible, sir. Clearly audible.
Thank you so much. Now, for the grid configuration, we usually conduct a size of 390 square mm. As I have told you, we have selected the flat of 65 into 6, that is 390 mm square, depth 0.6, grid length 30 by 18, and we have number of conductor we will be chosen 11 and 7. It has been given by the software itself, and the separation. These two figures will be given by the software itself. We feed to the software with all the parameters like this and this one, and obviously the ground resistance, ground potential lies how much,